Okay, so two announcements before we talked about the contents. First is there are two course evaluations during the semester, and I'm giving away 20 points if bonus points if 90% of students submit the evaluation. So for the middle term evaluation starts today, I guess, and it ends in a week. If 90% of the students submit the evaluation, so the whole class will get 10 bonus points. So there's no way for me to find out who submitted, who doesn't. So which means we need, right now we have 44 students, so it means we need 48 evaluations to get the bonus points. So previously, I've seen students on Slack to pushing this, ask others to submit, but there's no way you can find out who submitted or not. Okay, the second one is next week, we will have a midterm week. So both classes, we will do written exam and the CTF. So total will be 3 hours, 1.5 hour each session. So the CTF will be similar as what you did in the homework. We will give you several binaries, then the lady ask you to perform some attacks. And the CTF and the written exam has to be in person. There is no online option for this. Okay, today we keep talking about how to defeat stack-based buffer overflow, and it may take 2 classes to finish this. So before we move forward, let me remind everyone that attackers' ultimate goal is to take full control of the victim's computer. That usually means the attacker can run arbitrary code on the victim's computer. In some scenarios, this goal is too much to achieve. You don't have to run arbitrary code there. You just need to do something specific. For example, you steal a file, so you don't have to run arbitrary code as long as you can steal a file. So in this case, we assume the attacker wants to run arbitrary code there. To do there, usually the attacker needs to somehow hijack the legit control flow or redirect the control flow to his own code or his own share code. So on our server, the share code usually is just to print out the flag file. So to hijack the control flow, the attacker usually changes a code pointer using a buffer overflow or stack-based buffer overflow, change a code pointer. So for all kinds of attacks, you don't have to use buffer overflow to do that. In the rest of the class, we can say other attacks, you can also change a code pointer, but so far we're only talking about the stack-based overflow. So you see here, code pointer is a term that can actually cover many different things. The return address on the stack is obviously a code pointer because it's a return address. It's the address of the upper layer function and it points to code. So it's a code pointer. So overflow in the return address, you basically overflow a code pointer. However, you overflow the function frame pointer, which is the EVP RVP, which we saw last week. You do not directly overflow the code pointer, but eventually a code pointer, still the return address is overflowed. So the attacker can still get what they want. Also, in C, there is long jump, set jump operations. They are not really functions, they're more like macros, and they are architecture specific, the implementation of those. So in those long jump set jump buffers, the data structures are also code pointers. So if you can overflow that, you can also hijack the control flow. Obviously, function pointers is also a code pointer. And if how many of you program in C++? Not only C. Okay, so if you program in C++, the C++ classes, they have virtual tables at the beginning, and the virtual table has a lot of code pointers. So if you overwrite, so imagine if that class, the instance of that class is on stack, you overwrite that, then it's a stack-based overflow. But if that instance of class is not on stack, you use a new to create that object that will be on heap. You can still override it, so that will be a heap-based overflow. So those approaches you can use to overflow some code pointers. There are also other code pointers like a global offset table, which used by dynamic link. So you see that in the address space of a program, there are many code pointers. And sometimes the attacker only needs to overwrite one to fully take control of the computer. So it's very hard to defend, but a little bit easier to attack. So anyway, how can we exploit other pointers? Not only code pointers, but also data pointers. For example, memory that is used value to influence mathematical operations, conditional jump. So that is obviously not, let's say there is an address of a memory, and in that address we have a value, and that value we use to compare if it is some specific value or equal to or higher to some value. Like the very first local buffer overflow we did, overflow the local variable. So that local variable, its address, it's not really a code pointer. It's just a data pointer. But even things like that, if we can overwrite, we can still get what we want. We can attack. Some of the pointers we will only be used to read memory, not write to memory. So after we come back from spring break, in the format string vulnerability, you can see a lot of those pointers. We will be use those pointers to read arbitrary memory as long as it's mapped. However, we will not be able to write things there. Some of the pointers we can write, print as format string. There is a specific type, %n, we will be able to overwrite. So in real world, you sometimes combine many different vulnerabilities together, change them together one by one to achieve what your ultimate goal, which is get a flag or run arbitrary code. So there has been many attempts to stop buffer overflow, and at a very high level, we can categorize them into two types. The first category is about fully prevention of buffer overflow. So this category solves this problem directly, but the cost could also be very high, making it not very practical for real world programs. Because in real world, we care about speed. We want the programs to run very fast. The other category is to make exploit a little bit harder, but it doesn't really solve the problem. For example, last week, I give you a slide, I list those conditions that we need to pull off the attack. So if we take out one condition, so the previous exploit will not work, but the attacker may find another way to bypass that. It doesn't really solve the problem, but it slows down the attacker. Okay, so this kind of defense usually is very fast. The cost is very low. Usually very simple in theory, just some very simple defense, and they are widely deployed in real world. So today we are going to see several of those. So those approaches, they're not perfect. So they are also called the indirect defense. For example, base and bound check. This is a perfect solution that can prevent buffer overflow. A lot of high-level languages, they actually implement something like this. For example, Python, Java, in their virtual machines, they implement something like this. However, so in Python, Java, technically, you cannot do stack-based buffer overflow. However, they are very slow compared to, say, C++, assembly, or even Rust. They are very slow. Another approach we are going to look at today is a stack cookie. This is an indirect approach. It prevents overwriting return address if the attacker has a sequential overwrite ability. So this is a very simple approach. We're going to see it later. This is widely deployed. This is on all your systems. Most of the software you are using right now, this one, we are using this approach. This approach is published many years ago in a paper, and they are still very useful right now, but it's not perfect. Then last week we talked about data execution prevention. This one is also not perfect. We say how we can bypass this. Last week, we can use something like the return to libc to bypass this. So anyways, the buffer overflow one, the security property we are trying to achieve here is called a spatial memory safety. Because think about it, we put different buffers, different sensitive items on different memory locations, and we overwrite that. So we're talking about the spatial relationship. So there's a spatial memory safety problem. But since there is a spatial memory safety problem, there are also temporal memory safety problem that we were taught in the heap-based buffer overflow. So that one is the temporal memory safety issue. So for example, how can we make C as secure using that base and bound check approach? Let's say if there is a pointer A, so in this case, the pointer is supposed to point to a chart, but I mean, say you can point to anything, right? So you can point to anywhere. So for any of those pointers, the compiler can create a base and bound pointer for it. Let's say if we create a memory chunk and assign that memory chunk to A, then we will set the compiler will instrument code to set the base as A and the bound as A plus 512. So then any access using A must be between this range, A base and A bound. If anytime it's out of this range, the compiler instrumented code to tell that's not acceptable, okay? So if you access the 0 from 511, that's okay. But if you out of bound, overflow it, underflow it, the compiler at the runtime, compiler will insert the code. At runtime, the code will tell you this is illegal. But you can see this approach works. This is an approach that high-level language Java, Python use. But the cost of this is also very high. And also, if you assign this to different things, you need to clearly define the rule here. If you assign A to another pointer B, the B has to inherit the same thing as A, the same base and bound. Sometimes those rules will be very tricky to implement. Okay. But the overhead, like I said, the overhead is the main problem here. Well, when we write C and C++, we want it to be fast, almost as fast as you write assembly directly. But most people right now cannot do that anymore. But you can say to protect one pointer, we will need 2 more pointers. And every time you assign a pointer, there will be 2 more assignments to do this. And also imagine if whenever you access any data from that pointer, there will be 2 more comparisons to check if the access is legal. So that's why it's much, much slower. So this is a paper published in 2009, published in a conference called PLDI. That's one of the top conferences in programming language. PLDI stands for Programming Language Design and Implementation. That's one of the top conferences in programming language. And you can see that they implemented this approach back in 2009. But still, I mean, this is a well-cited paper in academia, but it doesn't really find its way into commercial state. The same team actually also published a hardware support to do the same thing, which will be a little bit faster, but still it requires some hardware support. And right now, real world, we're not using this. Okay, so that is about the direct defense, which is perfect in security, but bad in performance. So next, let's look at several practical approaches, which are not perfect, but has been deployed in real world, and also they are very hot areas in research. So the first one is called a shadow stack. I think right now GCC doesn't really support the shadow stack on x86, so I don't really have an actual code on our server to show you. But some other compilers, I think LLVM support that. We also implement shadow stack on small processors for our own research. So anyway, the purpose of a shadow stack is to protect the return addresses saved on the stack from being tampered. I took this picture from a 2015 paper. That paper was published in this conference called Asia CCS. This is a good software system conference. It always be held in Asia. That's why it's called Asia CCS. I think I probably mentioned several times in security, there are 4 top conferences. One is called CCS, Computer and Communication System Security. Another one is called Oakland, IEEE Security and Privacy. It's called Oakland because for the first maybe 2-3 decades, it was held in Oakland every year. But now they're actually moving south to Santa Clara area. Yeah, every year Santa Clara, but used to be Oakland, which is interesting because everyone knows Oakland is not a safe city, but that's where they host the best security conference. Then there's another one called NDSS, Network and Distributed System Security. The last one is called Usenix Security. So those are the top 4 security conferences for us. So Asia CCS is like a second tier, but still very good. So in the middle of this figure, we have a stack with 4 nested programs, functions. Okay, so this is our, let's see, this one doesn't really have any shadow stack. So this is a stack our previous program has been using. We have, let's see, do we have a name? So the stack goes from higher to low address, right? Let's say, so let's say this is a function 1. So the function 1 will have its, let's call it R1. R1 is not really the function name. Anyway, so here we have the parameter for that function. Then we have return address. Then we have saved EBP, right? So that's what we are familiar with. Then in this function may call another function. So the stack keep growing down. So then we have parameters, return address. This return address will actually be part of this function here. So here we have 4 functions. So we have 4 stack frames from upper address to lower address. The problem is if any of those variables can be overflowed, we may be able to overflow everything above that, including those return addresses, right? So the fundamental problem here is return addresses are code pointers. They are control information. And on the stack, we have local variables. They're just data. We're mixing control information with data. So the approach of shadow stack is to, let's separate them. We put the return address at a different location. We have a different kind. This is still kind of like a stack, right? But it's a different stack. It's not a normal stack here. The normal stack, we still have the return address, everything, but we're not going to use it. We're going to use the return address at a different location. We just put the return address here one by one, okay? So this is a traditional shadow stack. There's another approach. Well, traditional shadow stack, the problem is it's a little bit slow. Some paper report is like 10% overhead. To make it faster, but you see, this one's memory cost is very low. You are just storing some return address. The memory cost is very low. So another approach is called parallel shadow stack, in which the return address at the original stack and the new shadow stack, they already has a constant offset. Then everything between here is garbage. We do not care about this. Okay. The benefit of this is we can use this address, the original stack's return address, to find the actual return address in the shadow stack, which will be much faster. So later we're going to see the code. We can see why they are much faster. So this approach is widely used because the overhead is kind of like a 3%, very quite acceptable. Okay. So here I'm going to show you the implementation of this. So we can see here, let's see. So the whole page is for traditional shadow stack. Let's say we use the GS 108 as the shadow stack's pointer. So we have a pointer for the stack, which is SP, ESP, or RSP, right? So that one is still for the original stack. So now we're going to use another pointer, and this pointer we're using GS 108. So GS is another general register. Usually programs do not use this, but because usually programs do not use it, you can use it for many different things. Okay, but so this is what we're going to do. We first subtract the 4. So consider this whole thing as another pointer. This pointer points to our shadow stack's top. Okay, so we're going to push something here. That's why we decrement this shadow stack pointer by 4 bytes. We're still talking about a 32-bit machine. And then we move that new address to EAX. Then we move what ESP points to ECX. This program will be the new prolog for function. So this program is before that push EBP, move EBP to ESP subtraction. Okay. So at this beginning, what does ESP points to? This is right after a call instruction. So ESP points to the return address, right? ESP points to the return address in the original stack, right? Okay, so that's why we are moving what ESP points to ECX. So we're moving whatever is at that original stack's return address to ECX. Then we move ECX to where EAX points to. So what is EAX? EAX is GS108. So that is where our shadow stack is, right? So at the beginning of a function, we get the current return address from the original stack, and we make a copy of that to our shadow stack. So in our memory space, there will be two copies of the return address. One is the original stack, which could be overwritten. Another one is the is a new shadow stack, which still possible to be overwritten, but much harder. At least the approach we have seen so far, we cannot overwrite that. The approach we can see so far, they can only overwrite the original stack's return address. Okay. So at the end of the program, imagine that at the end of the program, attack may already happen, right? So the original stack's return address may be what? Maybe a malicious one, but we trust the one in the shadow stack. So what we're going to do is we just need to copy whatever we have in the shadow stack to the original stack. That's one approach. Another approach is we compare whatever is in our shadow stack with the original stack. So if they are the same, if they're not the same, we maybe just crash the program. Okay, so two ways, right? So let's say this piece of code. This piece of code, I think it's overwriting. So first, we get where the current shadow stack pointer is in ECX. Then we add for, it's kind of like a pop operation of the shadow stack. Then we move what ECX points to EDX. So what is this? This is legit, the real return address. Then we move this the real return address to ESP, to the original channel stack, then to the original stack, then we just return. Okay. So this approach obviously is not perfect. That's why this is an indirect approach. Why it's not perfect? Because the shadow stack may not be secure either. The shadow stack could also be overwritten by someone. Second, this approach doesn't compare that. So if they are not the same, we just write back the correct address. The program still may not work because other things, for example, local variables, other things may have been changed on the stack, original stack. So you can see this is a traditional shadow stack. You see how many new instructions we have to add there. 4 instructions at the beginning, at least 4 instructions at the end. And some of them could be quite slow, a lot of memory. So this one is actually a memory rate. So this pointer is actually not a register. GS is a register, GS108 is not really a register. So this is actually using a memory location as a pointer. So that is kind of stored. So, okay, so there's another approach is we do not overwrite, instead we check the value. So the same thing, we get the legit return value from the shadow stack, then we just compare that with whatever is in the original stack. So if they are not the same, then we just abort the program, otherwise we return, okay? So if you can say that if for every function, there will be several more instructions. I think I'm counting here. Okay. For the checking one, at the end is 6 more instructions, several memory moves, 1 memory compare, and 1 conditional jump. So that will make your program run much slower. Of course, this depends on how you write your program. You can have a huge function, or you can have a lot of smaller functions. If your functions are smaller, obviously the cost is higher because this is adding to each function. But from a software developer point of view, you want your programs, your functions to be smaller, not bigger, right? So then let's take a look at that parallel shadow stack. and say how do we implement that. And this is the implementation. You can see the implementation is much more, much smaller, very clean. We just assume the shadow stack, the one return address on the shadow stack, and its corresponding original one. They have a constant offset. Okay, so this is also at the beginning of the program. So ESP is ESP points to the return address, the legit of return address. We just pop it to the current address plus a constant. Then after that, we subtract the ESP again. So we still, because of pop, we can do this. We do the memory copy in one instruction. We're not taking it using the previous approach, putting it in a register, then move it to a memory location. We just use pop. But the byproduct of pop is ESP were +4. That's why we subtract ESP 4 again. So ESP still points to the old return address, the return address on the original stack. So the cost is here is only 2 instructions, 1 memory move, 2 instructions. The epilogue, obviously, same thing. You add it first, then you do a push. Okay, so that's why this is very fast. Like I said, some paper report that a parallel shadow stack overhead is like 3.5% in regular programs. Traditional one is kind of like 10%. Okay, any questions regarding how it works? Okay, so if you look at something like this, you will say, okay, doing research in security is not that hard, right? If you already know this, okay, how hard is it to move from this to this? Not that hard. If you are familiar with instructions, you mean familiar with how the Intel architecture or any architecture, you can come up with something like this. Then the performance will be 7% higher, and you can publish a very good paper. And this could be used in real world systems. Okay, so it's not that difficult to do research. Okay, the next difference we're going to look at is called stack cookies or canaries. Canaries. How do I pronounce this one? Canary? Canary? Okay. Yeah, I mean, there are several words I don't know how to pronounce. For example, yeah, go ahead. No, you're not going to implement this. Did you ask if you are going to implement this? No, you're not going to implement this. So for the stack cookies, you are going to write some code to exploit that, to hijack, to bypass that. For the shadow stack, we're not going to implement, because imagine, how do you implement that? You implement that by writing a compiler path. You basically change the compiler. The source code is not changed. Yeah, so it's the same source code. The same source code is automatically protected because the compiler will inject those instructions are directly injected there, or the word should be instrument there by a compiler. Yeah. So in our lab, we do a lot of those kind of things. We change compiler. We use the new hardware features. We find some new hardware features. We think about how we can use them. So we change compiler. The source code is not changed. Yeah. So this is a very popular approach all your systems are using. Shadow stack is not used everywhere. Most of right now are still just in academic projects, but stack cookies are everywhere. Your phones, your even very low-end IoT devices, their programs have this stack cookies. So this is a very, the reason for this is a very practical approach. Later you can say how simple this approach is. So this paper was published. This approach was proposed by several authors back in 1998. And the title of the paper is Stack Guard, Automatic Adaptive Detection and Prevention of Buffer Overflow Attacks, almost 25 years ago. So the idea is very, very simple. I think actually this paper, 10 years ago, this paper got the Test of Time award from Unix Security, which means after the paper is published, 15 years later, this approach was very, very successful in commercial tools in real world. So the committee gave the authors another award, Test of Time award. Getting an award like this is very, very difficult. When you have a paper accepted in those conferences, you already feel very lucky. Then 15 years later, people tell you, hey, you got a Test of Time award. That's something you cannot plan. Okay? Actually, in our department, I don't know if any of you took Dr. Marita Blanton's course before. She teaches crypto. She also, her research is also crypto. She also has a Test of Time paper award from another top conference, CCS. Very difficult to get. So in short, this is a compiler-based technique that attempts to eliminate buffer overflow vulnerabilities. But like I said, it cannot really do that. It's an indirect approach. It works in some cases. It's not perfect. So the technique doesn't require the developer to modify their code because it's compiler-based. The compiler will automatically patch the to-be protected functions, prolog and epilogue. So in the prolog, the code will do something very simple. It will push an additional value onto the stack. And that additional value is the so-called Canary there. Okay? That's just a 4-byte value in 32-bit, 8-byte in 64-bit. That's it. Then that Canary is placed right after the return address or saved EBP. Some places like that. So if you trying to overwrite the return address, you have to overwrite the Canary. At least the vulnerability we have seen so far. Okay. There are other vulnerabilities. You do not have to do a sequential overwrite. You can overwrite 4 bytes or 1 byte at any location you want. So in those attacks, this approach cannot defeat that. So then at the end of the function, we just compare if that Canary has been overwritten. If it is overwritten, then we just abort, crash the program. That is how simple it is. Okay. So this one I can show you demo and everything because this is widely used. We're going to use this program as an example, the overflow return 4. Let me remind you the program. We have a Vol here. Vol has some local buffer. Then we get some input for std_in, and this one we're supposed to overwrite things, right? Okay, so let's take a look at our server. So overflow 4, where is it? Oh, here. This is the old version which you exploited in your homework. We do a obj down here. And this is a Vol, very simple. You see, we find the buffer is at EBP minus 30, and this is that get function to override that. That's it. Let me open another tab here. Then the same program the same source code. If we compare this program with stack cookies, the program will look like this. Okay. First of all, compare those two. You can see we have many more instructions. Then let's take a look. What are those instructions? Oh, this one is a very old version. Some of the instructions not because of this. Okay, let me use my slide. So here we can see, we can clearly see what are the differences. The only difference is those 7 instructions. So let's take a look at those instructions. Here we are moving GS14 to ECX. This is a Canary version. Like I said, GS is a system, is also another general register. And GS14, GS is a register, so register has a value. GS14 is actually a memory location. Okay, that memory location has a Canary value, which is placed by the operating system there. So the Canary, the number, the value is not generated at compile time. Okay, I hope that makes sense to you. So if that value is generated at a compile time, then you can do a static analysis to figure out what that value is. Then when you override things, you just override the same value, right? So you can bypass that. So that value has to be a random value. So existing systems, right now, the system we're using, usually that is a random value generated when a program is launched, and it is only generated once. So all the functions, they're using the same value, in the same process, the same value. And that value is stored at the location GS14, which is a memory location. We can debug this a little bit later. So we get the value, we move that value to ECX, then we move that value to EBP minus C. That's it. So basically, we're in this piece of code, we are placing that Canary at EBP minus C. Then we clear what is in ECX. Then we have this program here. What if this program overwrites things? Then EBP minus C will change. The Canary will change, right? So that's why at the end of this program, what we'll do is we will retrieve at whatever is EBP minus C to ECX, then compare with the GS14 value. If they're not the same, then we call a function called the stack check fail local. Basically, that function will print out stack smashing detected, something like that. The GCC library will do that. Okay. So you can say this is kind of like you place an initialized local variable on the stack, and you have to make sure that local variable, when the program enters and the program exits, the function enters and exits, it has the same value. If it doesn't have a value, go ahead. This one? Yes, that's also a compare. Because they're supposed to be the same, right? So if they are not the same, the value will not be 0. Yeah, that's also compare. You can also use a compare instruction to do it. Yeah. So let's say if we run this program on our server, let's say, yeah, this is a version. How big is the buffer here? Let's take a look. Oops, well, what I'm doing. Let's say the buffer is, okay, because of that, the buffer is also changed a little bit, right? The buffer right now is EBP minus 34. 34 is 52 bytes, right? 52 bytes, okay? And the Canary is at a C. C is what? 12? 12, okay. So this one takes from standard in. let's just send some garbage to it. Let's say if we send 40 bytes, what will happen? 40 bytes, we're using gets. Gets will add a 2 there, right? Okay, gets will not add 2. Okay, so gets is perfect. So 41 bytes. If we send 41 bytes, we're supposed to overflow 1 byte of that canary, right? See? So when we send 41 bytes, we overflow 1 byte of the canary, and the program crashes. The GCC instrumented code will tell us stack smashing detected, terminating the program. Okay. So obviously, if you want to write many more, the same thing. Right? So you can say that those two, what are the differences between those two? We run the program twice. Once we give 41 bytes, the second time we give 61 bytes. So the first time, we didn't overwrite the return address at all. We only overwrite 1 byte of that canary there. But the second attempt here, we actually overwrite the return address. We can write the return address to whatever we want, but it will not be able to jump to it because we never have a chance to execute this return instruction. This return instruction is what we really put the target address into EIP. We do not get a chance to execute this instruction because before that, these 4 instructions, instrumented instructions, already detect the stack is overflow. So I think I need to show you a little bit about the makefile. Software code overflow 4. Okay. It's almost the same code. Here I make it 40 bytes, almost same. The difference is the makefile. Same as last week, what I showed you. Oops. You can say this is the first program, the overflow 4 program you hacked. So this program, I give it 4 options. The first one, M32, is to tell the compiler, let's compile this into a 32-bit one. This one, no stack protector. This is the one tell the compiler do not generate the stack cookies. Okay, so you can see that most programs right now will not give this option. So the default one is generate a stack cookie. Only if you tell the compiler do not do that, the compiler will not do that. Then this one is to tell the compiler the stack is executable or not. PIE here is not really important for us. Question? Yes, they insert those instructions. They insert those instructions. Yeah, of course. I mean, for example, this one is more complicated. This is actually a function, so you also have to insert some function. Yeah, but you also said that they insert this for all the instructions, all the functions. Not necessarily. Well, for example, if the compiler figures out this function looks very safe, there's no way this function has a bug or something, so they can all mix them to make it a little bit faster. Okay. But that requires a lot of static analysis. Yeah. So the one we are looking at now is yeah. Not necessarily. I mean, for example, let's say this function, there is one function. This one function doesn't have any input from user. However, this function calls another function. That function, well, you can, well, I think that's not necessary from user. I mean, if you take any input from anywhere, it will be dangerous, right? Even if you take input from a local file system, that would also be dangerous. So there could be some heuristics you can come up with. I think you are thinking in the right direction. You can come up with some heuristics to make sure you don't have to insert to every function to make it faster. But I'm not saying the heuristic you just said is reverse. It may not be very reverse. Yeah. So I think the program we are looking at is this one. Yeah. No, this one. Yeah. So this one, I don't have that long executable flag, or I don't have the low stack protector flag. That's why. Okay, so let's take a look at the 64-bit version as well. 64-bit version. I cannot get anything. So the 64-bit version, almost the same thing. The only difference is the Canary is not 4 bytes, it's 8 bytes, and the Canary is not at GS 20. It's not at GS 14 anymore. It's at FS 28. Okay. So that's the only difference. So you can see what we're doing here. We get the Canary to RAX, then we put that one to EDP -8. Then when we get out of the function, we retrieve from the stack, then we compare the Canary with that what we retrieve from the stack to reflect correct. Okay. So that is how Canary works. This is a simple approach, so we can defeat that. So that's what we're going to do. Today, probably we don't have time to do that, but Wednesday, we're going to write programs to defeat this. Okay, so this is, I draw this, but I already explained to you. So basically, the buffer, we just insert the Canary between the buffer and the saved EDP in our case. Obviously, there could be other approaches. You do not have to insert it here. You can insert it some maybe here. So you do not protect the saved EDP, only protect the return address. So the overhead you can see here is almost the same as stack cookies. That's why the performance is also kind of like 5-6% overhead. I want to talk a little bit more about those two values from GS14 or FS28. So like I said, GS, FS, they are registers. So GS common 14 actually is a memory location. FS common 28, that is also a memory location. That thing itself is not really per se, it's not really a register. So when the program is launched, the operating system or the library, doesn't have to be the operating system, the library to call that program will generate a random number, and the random number is stored at those memory locations. And this is only generated once, okay? So current implementation only generated once, so it's not that safe. And that FS and GS, they actually point to a data structure called thread context or thread local storage. That's a data structure to store the program related information. The data structure is called a TRS. So if we debug locally, we can use the TRS command to do that. But on the server, I guess we don't have that plugin to do that. Yeah, okay, we can debug this locally to show you. Let's do a GDB. We want to run this version, I guess. So we set a breakpoint, main, we run this program. So you can see on my local machine, I have all the plugins for GDB. That's why it looks fancier. It shows you all the register values. It shows you the code and also what the stack look like. So if you do TRS, it will show you the TRS's location, which is that this will be the same as what GS is, I believe. Let's see. Let's print out GS. Should be $sign here. Should we do this? How do I do that? I think I can do 14. So we should be able to examine them, right? Exam 4 bytes there. Why is syntax error? What should be the syntax? Like weird. Well, you can see I haven't done this for a long time. What should be? Well, this percentage sign is for. Oh, I think we should do plus. Let's see. Plus. No. Oh. No, sorry, plus. Hey, but our GS is at this address. That's weird. We're already running the program. Let me check if we're using the right program here. Oh, this is the right program. So this is where. Okay, let's set a breakpoint there. Here. So let's say we run this program, we are here, then we do a NI, next step, then we can get the Canary in the ECX. And you can see this is the Canary we are using in my current program. Something interesting here is for GCC, my version, the last byte is always 0. Okay, so actually only 3 bytes are random. The last byte is always 0. Okay, we're going to utilize that information to hack this. So obviously there are many ways to choose that Canary value. You can make it purely random, all 4 bytes, 8 bytes, purely random, or there are other approaches. For example, you just choose all of them as 0. This is also beneficial because those string functions, they will terminate at 0, right? Also, you can use other terminator canaries there, like zero, like new line, those kind of things. But the most popular ones I have seen so far is still random. Random 3 or 7 bytes. The last byte was 0. So let's say. So this idea was introduced in that Unix security paper I showed you. Then it was introduced as a GCC feature, a very old version GCC. Then there are other people developed new approach based on this. For example, IBM developed something called Pro Police. We're going to look at that soon. So that approach places buffer after local pointers on the stack frame. So to help avoid the corruption of pointers, we're going to see that soon. Some examples. Then Google also 2012, they implement a new flag called the Stack Protector Strong flag, which is a stronger version of the stack cookies. I think right now, Android is probably compared with this flag. And the flag I'm using on our examples are just the stack protector, not the strong version. And most system we're using right now, even the OS we're using right now, is compiled with this flag. Some of the Linux packages are using a strong version now. Okay, so let's take a look at this Pro Police approach created by Microsoft or IBM. Okay. So on the left-hand side, we have the C program. We have several local variables. We have an integer A. We have a pointer B. Then 2 buffers. Then after that, we have B will point to A. Then we are going to do a string copy from C to some other places. And that string copy. So if the stack is arranged like this, so this is by default how GCC or old compilers will arrange the stack, right? So whoever the local variable, whichever declared first, we're at a higher position because A is higher than B, C, D, right? So this is how it works. The problem of this is you can say C and D is a vulnerable local variable here. So it could be overflow. And if we overflow them, we will overflow everything, including A, B, and the saved EBP I return. So the Pro Police idea is to let's rearrange the order of those local variables. We do not follow the order the developer programmed there. Okay? So instead, we put a CD at the top, then AB. Then we put a canary there. The benefit of this is if we're using the default layout and we put a canary there, what will happen? We will still be able to overflow AB there, even though we cannot overflow, say, the EBP, whatever. Of course, another approach is you put the canary between a D and a C. That will also work, but that probably will require more program analysis, right? So in this approach, we have AB at the bottom, CD here. D may override C, of course. C will still may override the canary. Then the program will crash. So no way to override AB. So that is just a single approach proposed by IBM. Okay. So next, let's look at something something I really like in this class is the whole class. This is whole semester, this is one of the interesting I really like. Is how do we bypass this? How do we bypass this? Canary, any idea? No, it don't work. That's always the location. Yes. You cannot write it. Yeah, that's a location you can only read. That's good thinking, but you don't have the privilege to write it. Yeah, and also here we assume you only have the you only have the sequential overwriting ability anyway. So the idea here is we just guess. We just guess. Which value copy to be sent? How do you read from it? You need to insert some code to read that. Yes, but most of the cases you can. Let's say we're attacking Apache server. How can you debug that on that server? Right? You cannot do that. Okay. So basically, what we want to do is guess. But there are two things make this possible. The first one is a lot of program. Like I said, the Canary is generated when the program is loaded. Okay. If the program is forked to two programs, they will have the same color. Okay. But for servers, especially web servers, they are keep forking new programs. If you send the HTTP request to a server, the server may fork a program to handle your request. So if you programmed in socket before, that is how it works, right? You get a package, you fork a new program, and the new sometimes a thread, sometimes a program. Then if it's a new program, the new program will handle that. But because it's forked, they will have the same kind of. That is how we can utilize this feature to hack programs with canaries. Another thing is, if we want to guess, let's say canary with 3 bytes. The last byte we know is 0. Okay, in our implementation 0. So it's the 3 bytes. So if we guess, we guess from 0 to the maximum number. So it will take, hold on. It's 24 bits, right? 2 to the power of 24. That is how many guesses we are going to make to, yeah, go ahead. That's what I'm saying, because you create a new process. A new process where so we have a server program, like an Apache server. When you send a HTTP request to it, the Apache server will create a new process to handle your request. So when you crash it, you are going to crash the new process, not the old Apache main process. Yeah. So that's why you can keep some things there you will create. And every time you create the same process, have the same canary, that's why you can guess, right? But still, the number you're going to guess is huge. Let's say 32-bit version. We basically will have this is the same thing as 2 to the power of 24, right? So that's like you need to get we know the last byte is 0. Even though the last byte is 0, we are still going to guess 60 million times. For sure, we're going to get it 60 million times. So if we are able to guess once 1 second, that will take Well, once 1 second makes sense because we are trying to attack a remote server. You're considering the latency, considering the server need to create a new process. So 1 second is reasonable. So it will take 194 days to really guess that. Okay. But how can we speed this up? Is there any way we can speed this up? We don't have to do this in almost 200 days. We can do this in several minutes. How do we do that? What? Get 8 bytes? Okay. Yes, but that's this approach, right? So basically you're guessing 3 bytes every time. Do we have to really guess 3 bytes every time? If we get 3 bytes every time, this is how long it's going to take. But if we do not guess, if we do not guess 3 bytes every time, we only guess 1 byte at a time. We know there are 3 bytes of canaries. So the first time, we're only going to override the first byte. We're not going to override all 3 bytes. So the first time, since we're overriding 1 byte, how many times we need to guess? 256. Then eventually we can get it, right? Then we know what is the correct one. The second time, we override 2 bytes, with the first byte is the correct one. So we will take another 256 times for us to get it right? So worst case, technically we only need 700 something times to guess that. So when you guess, let's say 3 bytes there, you are going to override. You only override the first one. If the program crashes, you know it's not correct. If the program doesn't crash, you know you have the right value. No, you cannot do half. You cannot do half byte. You can only do 1 byte, right? You cannot override this 4 bits. You cannot do that. Yeah. So what do you mean by after zeros? Yes. I don't remember if that's least significant or most significant, but it doesn't really matter. Yeah, doesn't really matter there. Yeah. So you're saying if you get it right? Yes. Well, you're only going to override the first byte. The other 3 bytes you are not going to override, so they will not be changed, right? So you only need to get this byte right. So after you get this byte right, you override 2 bytes. Then the other 2 bytes you are not going to touch. Yes, right. Okay, does that make sense to everyone? Okay, so now we don't have time to do this today, but I will give you this is the program I developed. This is a program we are going to have. But I will explain this program a little bit because it's a little bit more complicated than the other program we have seen so far. This is called a bypass Canary program. It has a main function. The main function has a infinite loop. This program is just looping here. What it does is it will just fork. It will create another copy of itself. The parent copy will just print out, I'm the parent. This is a parent process ID. Then I'm going to wait for the child. That's it. It's not going to do anything else. The child will call the vulnerable function, the vol foo, and print out IP to the full. if you couldn't hijack this program, right? If you after that it will exit. So the parent to say, hey, the child exit, no matter the child exit because you crashed it or it print out IP the full, what will happen? It will create another child for you to hack. And the child will have the same canary, okay? Okay, then in the Volfu, the child, what it does is there is a vulnerable buffer, 40 bytes, and this one is protected by Canary, obviously, but you will be able to overwrite this. So what this program does is it will open a local file called the exploit. You just need to so you need to write your exploit to this local file. I didn't do this in a socket or anything, but it can be implemented that way. You can see that the Apache server is basically taking input from socket. This program is taking input from a local file, so it makes things a little bit easier. So if it finds there is a local file called exploit, it will just basically it will just read whatever you put there to the buffer. So it gives you the opportunity to guess the infinite number of opportunities. If it doesn't work, you will close the file, it will remove the exploit, then return 0. Okay, so this is how the program works. So I think we probably have 1 minute to run the program here. Yeah, so this is a program. The program running, you print out this. Let's say we can do we need 2 terminals for this. We have 2 terminals. The first one, we run this vulnerable program. The second one, what we can do is we can just echo something to exploit, right? Oh, we don't have permission here. Okay, I need to change this program a little bit because it's the first time I run this on the server. I need to, because we don't have the permission to run program here. I'm going to change it to the temp file. Okay, so this is what we are going to hack when we come back Wednesday. What? Why the fork the program has the same? Because when you do a fork, you basically make a copy of the program, the exact copy of the program. Fork is a system call, right? Well, you can say whoever is implementing that they can change the fork. The fork can have a different channel, but right now no one is doing that. Yeah. Other questions? Yeah. Why? Yes, but web servers usually is designed this way. Web servers is designed this way to get input to your fork, and that's why it's possible. Yeah, you cannot control the fork, but a lot of programs is designed this way, they will fork. Yeah. Okay, cool. See you guys Wednesday.